Hello friends, welcome to another lecture number 4 of Laplace Transformation, Mathematical Physics. So here we are going to discuss these topics here: Laplace transformation of derivative of f of t, and Laplace transformation of integral of f of t, and also we are going to discuss final value and initial value theorem, and Laplace transformation of t into f of t, that means multiplication of t with the function, and Laplace transformation of exponential integral function. Okay, so let us discuss those, and before that, please like, share and comment and subscribe this channel and follow me on Insta. My Insta ID is ozaloikajit123. Okay, so now let's start. Now Laplace transformation of derivative of function f of t. So we know that Laplace transformation of a function f of t is given by integration from 0 to infinity e to the power minus st f of t dt, right? So which is also represented by capital F of s, which is the function of s, right? So what if Laplace transformation of the derivative of this function f of t, that means f dash of t, derivative of f of t is the f dash t, right? So what will be its Laplace transformation? That is SL, that means here L stands for Laplace transformation of f of t minus f of 0. This is given by this theorem, right? Or you can write instead of Laplace transformation of this, you can write s capital F of s minus f of 0, right? Because Laplace transformation of f of t is given by f of s, right? So now let us prove this. First, Laplace transformation of derivative of f of t so is equal to s capital F of s minus f of 0. Now let us prove this. So now let us scroll down the page. Okay, so by definition of Laplace transformation, we know by definition of Laplace transformation, we know that Laplace transformation of f of t is given by integration 0 to infinity e to the power minus st f of t dt, which is also capital F of s, right? So we can write this way. So now you see, this is suppose 1. So Laplace transformation of f dash of t, that will be given by then 0 to infinity e to the power minus st now we will write here f dash of t dt, because we are going to find the Laplace transformation of derivative of f of t, that means f dash of f dash of t, right? So by definition we should get this, right? So here you can see, now we are going to apply this. So consider this is as u and this is as v, first function and second function. So you know this rule, integration of u v dx is equal to u integration v dx minus integration derivative of u, then integration vx dx, v dx and whole into dx. So we know that. So if you apply this here, then what you will get, ignoring the limits, let us take this one only, integration e to the power minus st from the right hand side f dash f of t dt. So what we are going to apply, we are going to apply this integration u v dx, which is given by u integration b dx minus integration of whole u derivative of u integration b dx. So let us apply this. Now consider this one as u and this one as b. So then what you will get, if you do so, let me scroll down, then what you will get e to the power minus st integration f dash of t dt minus integration within the square bracket, you will get derivative of e to the power minus st, then integration again f dash of t dt, then bracket close, again dt. That's what you will get, right? Now let me scroll down the page. Okay, so now here you can see, next we will get e to the power minus st. If you integrate f dash of t, then you will get f of t, right? So because f dash of t means derivative of f of t, therefore integration of f dash t dt must be f of t, right? So hope you have understood this. So now integration and derivative of e to the power st is given by minus s e to the power minus st, and integration of f of t again, that will be, integration of f dash of t, that will be again f of t, right? F of t, then we have dt here. So hope you have got it. Now let me scroll down the page. Okay, now e to the power minus st f of t. So here this minus it will be plus integration, and this s should be taken outside the integral, right? Integration e to the power minus st f of t dt. Now here you see, by definition of Laplace transformation of f of t from equation number 1, you can replace this part by what? Laplace transformation of f of t, right? If I am not wrong, you can replace this. So let's do that. Then what you will get? Then you will get e to the power minus st f of t plus s into Laplace transformation of Laplace transformation of f of t, right? You will get that from 1, right? From 1. So that is what we have got. Now let us use this integral result here. Let us use here, then we will use the limits. Okay, so now let me scroll down. Then what you will get, Laplace transformation of f dash of t, that's going to be equal to e to the power minus st f of t, and we have the lower limit 0, upper limit infinity, plus s Laplace transformation of f of t, right? Now here you see, when you put infinity here, then it's gonna be 0, and when you put here 0, e to the power 0 will be 1, and 1 into f of and this t also should be replaced by 0. Okay, then what we will get? We will get, let me scroll down the page. Okay, so on putting the upper limit, you will get here on 0 minus, and putting the lower limit, you will get this will give 1, and this will give f of 0, right? F of 0, and plus s into Laplace transformation of f of t, right? So or you can write this way: Laplace transformation of derivative of ft or f dash of t is equal to s into Laplace transformation of f of t minus f of 0, or you can write s capital F of s, because Laplace transformation of f of t we have we have considered as f of capital S, right? So capital S into capital F of s minus f of 0. So that's how we can prove. So hope you have understood this. Now now let's move on to next, that is our Laplace transformation of integral of f of t. Okay, let us discuss that. Now Laplace transformation of integral of a function f of t. So Laplace transformation of integral 0 to t of a function f of t dt, right? So what will be its result? Its results 1 by s capital F of s, okay, where capital F of s is nothing but Laplace transformation of f of t, right? So now let us prove this. So let us suppose that phi of t is integration 0 to t f of t dt. Let us consider it as phi of t. So phi of 0 is 0, and derivative of phi of t. So here you see, if phi of t is integration of f of t dt, then derivative of phi of t, that's gonna be f of t, right? That's gonna be f of t. So now what will be the Laplace transformation of derivative of phi of t? Laplace transformation of derivative of phi of t, that's gonna be given by so we have already discussed that Laplace transformation of derivative of f of t, that is given by s into Laplace transformation of f of t minus f of 0, right? If you apply this here, then what you will get? If you apply this, then what you will get? S into Laplace transformation of phi of t minus phi of 0, right? Minus phi of 0. So that's what we will get. So as we have phi of 0 is 0 here already, so this term will be 0, right? So that's why we get here, let me scroll down the page a little bit. Okay, s into Laplace transformation of phi of t minus 0. That means you can write this only: Laplace transformation of derivative of phi of t is equal to s into Laplace transformation of phi of t, right? That's what we will get. So if you simplify this, then what you will get? Laplace transformation of phi of t will be equal to 1 by s and Laplace transformation of derivative of phi of t, right? That's what we will get. Now what is phi of t? Phi of t is integration from 0 to t of f of t. So that's why let us replace this. Phi of t is integration 0 to t of f of t dt, right? That is phi of t. So we have replaced this phi of t, and we have assumed here phi of t is integration 0 to t f of t dt. That's what we have put here. So 1 by s and Laplace transformation, and derivative of phi of t is nothing but f of t. So let us put this here. So then what we will get? Laplace transformation of f of So this is the theorem, and Laplace transformation of f of t is nothing but what? Laplace transformation of f of t, we have assumed capital F of s, which is a function of s. Here it is mentioned, right? So that's why. Now if you replace this Laplace transformation of f of t by f of s, then our result is Laplace transformation of integration of 0 to t f of t dt 1 by s, that's into capital F of s. That's how we can prove. So hope you have understood this. So now our next topic is initial value and final value theorem. Okay, now let us check what is there. Now initial and final value theorem, if Laplace transformation of f of t is capital F of s, which is a function of s, then by the initial value theorem, says that limit f of t when t tends to 0, is equal to limit of s into capital F of s when s tends to infinity. Right? Let me write it properly. S tends to infinity. This is by initial value theorem. Okay. So now, and by final value theorem, says this limit of f of t as t tends to infinity, limit of s into capital F of s when s tends to infinity. So remember this. So sorry, not s tends to infinity, s tends to 0, right? So this is by initial value theorem, and this is by final value theorem. Now let us prove these two one by one. So first let us prove the initial value theorem. Now you see Laplace transformation of derivative of f of t, that means f dash of t, is given by s into L, s into Laplace transformation of f of t minus f of 0. That is already we have proved, right? So now you see, let me scroll down the page. By definition of Laplace transformation of this f dash t, we should get 0 to infinity, integration 0 to infinity e to the power minus st f dash of t dt, right? That is what we should get, is equal to, and we know Laplace transformation of f of t is nothing but capital F of s, so we can write s into capital F of s minus f of 0. That's what we should get. Now this is suppose equation number 1. Now let us take limits on both sides in order to prove this initial value theorem. Let us take limits on both sides for s tends to infinity. So then what we will get, taking limit of integration 0 to infinity e to the power minus st f dash of t dt when s tends to infinity, is equal to limit s tends to infinity, limit of this s into capital F of s minus f of 0. Okay. So now what we will get? Now here you see, in this case, let me tell you one thing. Okay, as here you can see, this is the only function of s on the left hand side. That's why we can write this way. Let me scroll down. Limit integration 0 to infinity, limit s tends to infinity, e to the power minus st, and into f dash of t dt. That's what we can write. So hope you have understood this till now. And this can be written as here this is function of s, so we can write limit s tends to infinity, capital S into s into capital F of s, and minus, not minus, yes, not yes, it is minus f of 0, right? We can write this way. Now, as we know that limit, so remember this result, limit when s tends to infinity, e to the power minus st is equal to 0, then so here we will get this part is equal to 0. This is nothing but 0, right? So we will get here, it is integration, this left hand side will be 0 as this results become 0, limit e to the power minus st when s tends to infinity, that's going to be 0. So that's why this left hand side part will be 0, right? So now we have got limit when s tends to infinity, s capital F of s minus f of 0. So this can be simplified as f of 0 limit s tends to infinity, s capital F of s. Now f of 0, it is nothing but when you will take limit of f of t, and when t tends to 0 we will get f of 0, right? So hope you have understood this. So instead of f of 0 we can write limit t tends to 0 f of t, right? That is equal to limit s tends to infinity, capital S capital F of s, right? So this is the initial value theorem. So that's how we can prove, right? So now let us prove the final value theorem. So this is initial value theorem. So to prove the final value theorem, let's go back to equation number 1. So here you see, to prove initial value theorem we had taken limit s tends to infinity here, right? And to prove the final value theorem we are going to take the limit when s tends to 0, okay? S tends to 0. So again taking limit on both sides of this equation number 1. So what we will get, let me rewrite the equation number 1 here again. So what is the equation? 0 to infinity, integration 0 to infinity e to the minus st f dash of t dt, and s capital F of s minus f of 0. That's what this is the equation number 1. So now let us take limit on both sides when s tends to now we are going to take s tends to 0. We are going to take this s tends to 0, right? So limit when s tends to 0, integration 0 to infinity e to the power minus st f dash of t dt, right? And limit of this s tends to 0, limit of s capital F of s minus f of 0. So now here you see the left hand side, it can be written as 0 to infinity limit s tends to 0 of e to the power minus st f dash of t dt. So here limit s capital F of s tends to 0. So it is already f of 0, so we can write directly f of 0 here. It's not a function of s now, so that's why we can write this way. So now you see what we can do. So Laplace limit s tends to 0 when limit of e to the power minus st s tends to 0, it gives 1. This is equal to 1. Okay, so we can write here limit s tends to 0 when e to the power limit of e to the power minus st when s tends to 0, it gives equal to 1, right? So let us use that value here. So if you use that value here, then you will get integration 0 to infinity 1 into f dash of t, that is f dash of t dt, right? You will get that. Then limit f of s when s tends to 0 minus f of 0, right? Now you see, if you integrate the f dash of t means what? Derivative of f of t, right? Which is f dash of t. So that implies what? Df of t f dash of t dt, right? So if you integrate this, then what you will get? You will get integration f dash of t dt is nothing but f of t, right? You will get if you integrate both sides, then you will get f of t, that is equal to integration f dash of t dt, right? So that is what, if you put here limit 0 to infinity, then what you will get? Here you will get 0 to infinity. So now we have f of t 0 to infinity limit s f of s when s tends to 0 minus f of 0. That's what we will get. Now if you use the limits, then what you will get? F of infinity minus f of 0, right? Minus f of 0, then limit s tends to 0 as capital F of s minus f of 0. So here we can cancel minus f of 0 minus f of 0, right? So finally what we can write? So f of infinity, it can be written as limit f of t when t tends to infinity, that is equal to limit s f of s tends to 0. So this is the final value theorem. So hope you have understood. That's how we can prove. So now let's move on to next topic. So our next topic is Laplace transformation of t into f of t. Okay, Laplace transformation of t into f of t. Transformation of t into f of t, that means multiplied by t. Okay, multiplication by t. So hope you have got it. Multiplication by t. Right. So now you see, this theorem says that if Laplace transformation of f of t is capital F of s, then Laplace transformation of t to the power n f of t is equal to minus 1 to the power n, and nth order derivative with respect to s of f of s. Okay, so that is what this theorem says. Okay, Laplace transformation of f of this, okay, multiplication of t. So now here you see let us prove it. So let me scroll down the page. Okay, so here we know that by definition of Laplace transformation of f of t, it gives capital F of s, which is nothing but 0 to infinity e to the power minus st f of t dt, right? That's what we get. This is suppose equation number 1. Okay, now if we differentiate with respect to s, okay, differentiating with respect to x, differentiating with respect to s, we get, so what do we get? If you differentiate, you will get d by ds of f of s, and similarly derivative of this with respect to s, 0 to infinity e to the power minus st, so f of t dt, right? So here this is not a function of s, f of t, it is function of t. So here we are going to use the partial derivative. So it can be written as integration 0 to infinity, so del by del s of e to the power minus st, so f of t dt, right? That's what we can write. So now here you see, so derivative of this with respect to s is given by 0 to infinity minus t e to the power minus st f of t dt. That's what we get, right? So now you see what we can do here. We can take out the minus sign and we can write this way: 0 to infinity e to the power minus st into t into f of t dt, right? We can write this way. So hope you have understood this. And if you observe, if you compare with the definition of Laplace transformation, that Laplace transformation of f of t is given by integration 0 to infinity e to the power minus st f of t, right? F of t dt. So here you see, if you compare this result with this, then what you will get? This is our f of t now, right? And this is e to the power minus st. Then according to that, we used to get, now instead of f of t we have t dot f of t. That means it is nothing but Laplace transformation of t dot f of t. That means multiplied by t with f of t. So that means we can write minus Laplace transformation of t dot f of t. That's what we can write by definition of Laplace transformation. By definition of Laplace transformation. Understood? So hope you have got it. Now this is nothing but dds of f of s, right? So now what we have got now, that here you see, let me scroll down, derivative of here it can be simplified as Laplace transformation of t into f of t dt is equal to, we can write minus dds of f of s, right? We can write that way. So now you see, now if Laplace transformation of t to the power 2 is multiplied with f of t, then what we will get? Then we will get positive d by ds of that should be now second order derivative of f of s. That's what we will get. Okay, so now you see, we can assume this is -1, and then we can assume this positive as -1 square. Similarly, if you find Laplace transformation of t cube into f of t, then you will get -1 whole to the power 3 third order derivative with respect to s of capital F of s. That's what we will get, and so on. That's why we can write that Laplace transformation of t to the power n into f of t minus 1 whole to the power n and nth order derivative of f of s with respect to s. So that's what we have got. That is what we need to prove. So hope you have understood this. So this is very simple, right? So n means here, n means 1, 2, 3, so on, right? So now let us discuss the last topic, that is exponential integral of function. Now Laplace transformation of exponential integral function. Now you see, Laplace transformation of integration t to infinity e to the power minus x by x dx. So what will be the Laplace transformation of this? That's given by log of s plus 1 and divided by s. Whole thing is divided by s. Okay, so here you see, let me show you how to prove this. So let us consider that f of t, let us consider this function is f of t, t to infinity e to the power minus x by x dx, right? Let us consider it this way. Now here you see, let me take an example. We know derivative of sin x is cos x, right? And integration of cos x dx is sin x. That's also we know. Now if you compare this situation with this, so we don't need these results here in this problem. Just I have taken these examples to explain this situation. Here you see, if the integration of this function is f of t, like integration of cos x is sin x, so then derivative of sin x is what? Cos x. Derivative of sin x is cos x. So that's why if integration of this function is f of t, then derivative of f of t must be equal to this function e to the power minus x by x. So as we have limits here, so use those limits, infinity to t. Okay, and if you put the upper limit and lower limits, what you will get? So f dash of t, then putting infinity you will get 0. Okay, if you put infinity here instead of x, then you will get 0, and if you put t, then what you will get? Minus e to the power minus t by t, and you can write minus e to the power minus t by t. That's what you will get. So we can write t into f dash of t is equal to minus e to the power minus t. Now let us take Laplace transformation. Let me scroll down please. Laplace transformation of t into first order derivative of f of t, that is f dash of t, and Laplace transformation of this can be written as minus Laplace transformation of e to the power minus t. Now here you see, from here to proceed we need to be very careful. Now you see, now listen carefully what I am going to explain here. It's very important. So here you see, we know that Laplace transformation of first order derivative of f of t, that is given by s, capital F of s and f of 0, and we have also got that, so let me use it. We have also got that Laplace transformation of multiplied by t, the with the function f of t. So before writing that, let me write, if we have already got that, if if Laplace transformation of f of t is capital F of s, then Laplace transformation of t into f of t is given by first order derivative minus first order derivative with respect to s of f of s when Laplace transformation of f of t is f of s. Now what we have t into f dash t, not f of t, f dash of t. Then what we will get? So here you see we have got this result minus ds or minus first order derivative of f of s when Laplace transformation of f of t is capital F of s. So but Laplace transformation of f dash t, first order derivative of ft, is s into capital F of s minus 0. Then if you find the Laplace transformation of t into f dash of t, that means first order derivative of t, then on this side minus d by ds, this f of s should be replaced by this result, right? That is s into capital F of s minus f of 0, right? So hope you have understood that. So now, so what we're going to have here, so our result will be this way. We will get minus first order derivative with respect to s into capital F of s minus f of 0, then equal to minus, we know that Laplace transformation of e to the power minus t, that's going to be 1 by s plus t, s plus 1. Okay, it's a basic formula. So here you see this minus sign gone. So we have derivative of first order derivative with respect to s of s capital F of s, and derivative of f of 0 will be 0 as it is constant. So we have got 1 by s plus 1, right? Now this can be written as, so let me scroll down the page, d s of capital f of capital S, d into f of s capital F of s is 1 by s plus 1 ds, right? So if you integrate this, integrating both side, what we will get, integrating both sides, we get s capital F of s is equal to integration 1 by s plus 1 ds, that is nothing but log of s plus 1 plus c. C is nothing but integrating constant. This is equation number 1. Okay. So now here you see, let us take limits now. Now we are going to find use the final value theorem. If you take limit s tends to 0, s capital F of s, on the other side limit s tends to 0 log of s plus 1 plus c, then what you will get? Now here you see c is constant, so constant remains constant, and if you find a limit of log of s plus 1 when s tends to 0, then you will get log of 1, and log of 1 is nothing but this is equal to 0. So finally we will get only c. And limit of if you use the final value theorem, according to final value theorem, limit of s into f of s when s tends to 0, it gives what? So before we use the final value theorem, yes, according to final value theorem, it gives limit t tends to infinity, limit of f of t, limit of f of t when t tends to infinity. And from here you see as log of 1 is 0, that's why we will get c only here, right? So this is what? By final value theorem. So hope you have understood. So we have already discussed about final value theorem, right? So now you see, we know that limit t tends to infinity. We know f of t, we have considered what? Nothing but t to infinity e to the power minus x by x dx. That is what? F of t, right? That we have already considered. Since f of t is equal to integration 0 to, sorry, not 0 to infinity, t to infinity e to the power minus t, sorry, in e to the power minus x by x dx. So that's what we have used here. Okay, now if you see that when when t tends to infinity, when this t tends to infinity, this is gonna be equal to 0, right? Its value will be 0. So then we will get c is equal to 0, because when t tends to infinity, the limit of this function will be 0. So hope you have got this. Now let us put c equal to 0 here in this equation, number 1. So what we will get? Putting c is equal to 0 in equation number, so here let me write this is 0. In equation number 1, we get what is the left hand side? S into capital F of s, s into capital F of s, and here on the right hand side we have got log of s plus 1 plus c. So c is 0 here, so we have got only log of s plus 1. Now here you see capital F of s, it is nothing but 1 by s log of s plus 1. That's what we get, right? So f of s is nothing but Laplace transformation of f of t, right? So, or you can write log of s plus 1 by s. So here remember, Laplace transformation of f of t is what? Capital F of s, right? So, and we have already considered that f of t is t to infinity integration e to the power minus x by x dx, right? So let us replace this f of t by this integral value, exponential integral of f of t, exponential integral function e to the power minus x by x dx, right? So that is what? Log of s plus 1 by s. So that's how we can prove. So hope you have understood this. So thank you for watching. So if you like the video, please hit the thumbs up button and share with your friends and subscribe the channel. So thank you for watching.